Not yet.
Not yet.
Okay, I will rejoin this.
By the time he'll be back, I have shared two links of two apps. You can download those apps.
Is it visible now?
Yes, yes. You can
Thank you.
continue.
So I will start with, as I was saying, that I will start with the quote of Benjamin Franklin. Tell me and I forget, teach me and I remember, involve me and I learn. And as Dr. Lakotia was telling you, that he has shared these links to download. So there are some apps which I'm going to use throughout the talk. One is this science journal. Earlier it was actually developed by Google, but now it is taken over by Arduino. The second one is Firefox, which is a German university. It is developed by Sebastian Stock and his team from a German university. It is very hard me to pronounce these names, so I apologize for that. Uh, Rather than embarrassing myself, there is one app called Wave Editor. It is on Android. There is a counterpart in iOS. This Wave Editor is not on iOS, but there is another app in iPhone. It is called Twisted Wave Recorder. You can use this. Both will have similar functionality. And these two on the top, you can forget for the moment. But I would like you to download at least Arduino Science Journal and the Firefox app. Okay, so while talk is on, you can start downloading that, and at one point you may want to use that. Govind, am I audible properly?
Yes, yes.
Okay, thank you. So what a smartphone can do in a physics lab, as Dr. Sanjay was telling us that in those earlier times, actually, it used to take 6 minutes, 6 rupees to make a phone call. And in the beginning, there was, phones which was of size of, almost like a slipper. We used to call that slipper phone. Then for last 2000 years, we were without without a phone. Actually, almost like without a regular phone in our life. But now it is so ubiquitous that we can't even think about having a without our life without a smartphone is almost, we think that there's something is missing in our life. And when you use a smartphone in your class, you will be scolded by your teacher because it is mostly distracting. You are using it for social media, you are using it to contact others. But as a student, you can always, think of innovative ways to harness its potential. What a smartphone can do. Have you ever thought about that? Maybe I will brighten up your mind with that. You actually carry a lux meter. Lux meter means which can measure the intensity of light. A sound spectrometer means which can measure frequency of sound for this obvious use. And a decibel meter means intensity of sound. Magnetometer, which is like measuring the magnetic strength of a magnet. Barometer to measure the pressure around phone. Thermometer and accelerometer to measure the acceleration. All in your pocket, and you don't have to pay anything for that because you have already paid for it, and everybody needs one nowadays, so it doesn't cost you anything. But I want to warn you here that some of you may think that now this can replace our regular measurement techniques in a lab. It is not of the case, because some of the measurements done by these kind of devices, they are of reasonable accuracy. Often you just want to verify a scientific principle, say that you just want to verify F is equal to m into a. But if you want to measure accurate values of force, mass, and acceleration, probably this will not be the best device to use, because you will just have some, it will not be good for a precise measurement. So just keep that in mind. What I'm going to do here in next 1 hour or so, I will exploit each sensor on a phone. Whatever I have an Android phone, so I will use that. I will start with the accelerometer. I will go for frequency sensor, then I will also use a decibel meter, and then light sensor, magnetometer, and see if I can perform some experiments using this. If time permits, then I will also give you some kind of assignment, and we will try to do something online here. So these are the apps which I have already introduced you. Hope you have downloaded these phones, these apps so far. So I will start with the accelerometer, which is I want to discuss here is the free fall. What is acceleration? I'm told that some of the students are from middle school level, so I will just take 1 minute to describe what acceleration means. It means it measures the change in velocity in time. So unit of velocity is meter per second. If I am measuring the change in velocity, then in every second, what is meter per second is changing. That's what accelerometer measures. Where do you use in your device? When you tilt your phone, then how does your phone know that it has to go from portrait mode to landscape mode? Okay, there's something called auto rotation. There it uses at this accelerometer. When you are navigating, how does Google know that you have taken a left turn, you have taken a right turn? There it uses the combination of gyroscope in your phone and an accelerometer. And your phone can measure acceleration along all three directions, namely X, Y, and Z. On the left side, what I'm showing you here is the direction of axis, the coordinate axis, which is defined in this accelerometer. It is if you hold up your phone vertically up, then up direction, the front direction, which is pointing towards the sky, is Y direction, and it is coming away from the phone, it's Z direction, and towards the width of the phone, that is X direction. How do they measure this? There is actually a small mass suspending between two plates inside the accelerometer, and there are some springs attached to these plates. So these plates actually work like a capacitor. So when phone is accelerating, so the mass also moves, the suspended mass also moves, and that causes the change in the capacitance between these two plates. So by this precise measurement, by this measurement of capacitance, in turn it gives you acceleration. That's what is inside that. But you can always use these kind of sensors just like a black box. You don't need to know how it is working. This is just good for common knowledge. So, but nevertheless, we just want to use the final values here. So you don't need to worry about how it is working. I just wanted to tell you. And if you just drop something, I actually, even when you are sitting right now on when you are sitting, then the acceleration due to gravity on you is 9.81 meter per second square. So for any object falling towards Earth, its velocity changes 9.81 meter per second in every second. So while you're sitting, actually you're falling towards Earth, but there is a surface, so you're not falling towards the center of the Earth. But acceleration, gravitational acceleration on you is 9.81 meter per second square. Now I want to verify that. So I want to use the Firefox app here. Some people call it Firefox. So if you open Firefox screen, it will look something like this. So you will see acceleration without G, acceleration with G. There are other sensors here, but you don't need to worry about that right now. Acceleration without G, it means it will give you raw value of acceleration. Okay, what is how your phone is moving? If your phone is moving with, let's say, acceleration 2 meter per second square, it will give you exactly value exactly like that. And when you want it to subtract that 9.81 meter per second square, you can use the value, you can use this tab acceleration with G. So when you are measuring the acceleration with G, it is actually already taken into account 9.81 meter per second square, which is the default acceleration due to gravity, which is the default acceleration acting on your phone. So when I click on acceleration without G, and what you can do, you can place the phone on the floor. Okay, just place it. And then if you go to acceleration tab without G, without gravitational acceleration, so you can see that linear acceleration. So since nothing is moving here, So the acceleration will come out to be 0 meter per second square. Okay, but you want to measure the gravitational acceleration. So you go to acceleration with g, and there you can see in the z direction, since it is lying flat, so the direction, z direction is coming out of the form. Hence, only the z acceleration value will come out to be close to 9.8 meter per second square. Okay, so there is x value, there is a y value, there is a z value, and if you square all these square individual x, y, z components, add those, take inverse, take square root, then the value will come out to be 9.85 meter per second square, which is the absolute acceleration. So this is very simple measurement, nothing great here. Now, how you want to verify the claim that when something is falling, then its acceleration is 9.81 meter per second square. So I will play a short video clip here, and let's see if I can. Okay, this is when it is at rest. Okay, so you can click on this Fox app, go to this. That's how the screen will be in front of you. You've already downloaded it. You click on this acceleration without g. Inside that, and you can see this triangle button here. You click on that, and that app will start. Okay, now you can also see this pause button here. You click on that, and your phone will stop taking the readings. There are other tabs like graphs, absolute, multi. If you go to multi, it will show you the value, numerical value. Instead of a graph, it will show you the numerical values. You can start it, pause it, and then you can go back. You can export this data anytime. You can go with acceleration with G, second tab, where you want to verify what is the acceleration acting on it when it is at rest. You go to multi-tab, and then you can see I already showed you the screenshot of this video. Okay. Now, when it is falling. So on right hand side, I will be performing the experiment. On left hand side, I'm showing you the screenshot of actually the screen recorder of my app. So I'm holding it just in a vertical direction. So it will measure. So what I'm interested in, since the direction of acceleration, the Earth is obviously here, so and it is pulling towards it. So I will expect this direction to come out to be 9.81, close to 9.8 meter per second square. This is y direction. Okay, the way Fox F has defined, this is the y direction. This is x direction, and vector coming out of its plane is z direction. I will just leave it. Be careful. Do not break your phone in this experiment. These stunts can be performed at home, but I will pause it. I will go to this recorded reading, and I have to locate where the phone was falling. So I went to this linear acceleration y. Okay, and this is the part where I'm interested in, where I can see that acceleration was not almost like constant. It was going from 9.4 to 9.6 to 8.89. Somewhere here it is started actually when it you can see this peak here. At this point, actually, it collided with that cushion. Okay. You can zoom it. You can click on any point on the curve, and you will get the real values. Okay, so you can see that this acceleration was close to 9.8 meter per second square. So that was all about accelerometer here. Now, where I can use it, this is just the raw value here. Of course, you can carry out many experiments here, but I was also told to carry out some biophysics related activity. So I will do a small activity here related to X reaction time. Reaction time is actually your response to some stimulus. Okay, I suppose I ask you to raise your hand when I say jump. Okay, and how quickly you hear that and you respond to that, that will be called a reaction time of your senses. Okay, you may remember in Indian cricket team who has the shortest reaction time. Hmm? Yeah. So look at Captain Cool MS Dhoni, and his reaction time was told to be the shortest. Okay. Let me see if it can run. Yes, yes, it can run. So how much time did it take for him to catch this? And Kuldeep Yadav bowled, and you can see when the ball left, it was distance between ball and MS Dhoni was 92 centimeter, and he was quick enough to catch it because his reaction time is, oh my god, it is written 0.08 second. It is very, very small. What is your reaction time? Hmm? How to measure this? You can use this accelerometer app to measure your reaction time. So this activity was, this is not a very recent activity. What we do in our class, actually we drop a scale and ask someone to catch that scale. And how quickly you catch that scale, that will be called reaction time. So I have changed it slightly here. I'm dropping my phone here and my wife is trying to catch it. So I'm not telling her when I'm dropping. She has to see when it is started dropping and she has to catch that. And the time it is in air, or the time when the phone is in air, is acceleration will be 9.8 meter per second square. And I just have to measure the time for which the acceleration was this acceleration due to gravity. And that will be called the reaction time of whoever is trying to catch this phone. So I will show you the video for it. Uh, okay, on left side again, the screen recording, and right side I'm performing the experiment. So I am holding this phone away from the fingers of this person, and I will just drop it without warning her, and she caught it at some point. Great. Before it could strike the surface, now I will go to this linear acceleration y, and I have to locate that segment where the acceleration was almost constant. It was close to 9.81 meter per second square. So this flat line, what you are seeing, is our data of interest. So at this point, when it started, so 4.39 second, at 4.39 second, phone started to drop. And at 4.52 second, she caught it because after that, acceleration change. So she caught it from 4.39 to 4.52, which is like 0.13 second. Wow. My wife is actually, it looks like she has very good reaction time. She can beat Dhoni. That is almost like 0.15. It is not far away. So you can perform this activity at home. Okay, just be careful to put up secure your phone using a cushion or some pillow, so that if you are not able to catch it, if your reaction time is large, if you're not able to catch it, you should not break your phone. there are some apps already on Google Play Store. They're called Reaction Time. They have a different mechanism. So I just advise you to download this app and use that. I'm sure there will be similar on iPhone also, which I have not explored yet. So this is one activity here. Now using the decibel meter, because your phone obviously it can be used for actually the most harnessed sensor used in phone is sound sensor, which can measure your frequency, which can measure the decibel, which can measure the intensity of sound. So I want to use it to listen to your heart. How do I do that? It is very simple. It is actually this. I think this is one of the greatest exercise I have found, which combines smartphone to medical science. You can use a headphone, or you can, since it has to be not very close to your chest, so you put a double-sided adhesive tape, and you do not cover the mic of your headphone, the mic part of your phone. You can see I made a hole here, and then I have fixed this double-sided adhesive tape to on the mic part of this headphone. And I'm using this app called Think Labs Wave. You can use some decibel meter also, but this phone has this app has some advantage. It gives you intensity, as well as it gives you the frequency pattern of this of the sound. So you hold this headphone close to your chest, obviously on the left side, where you can hear the heartbeat very closely, and you keep it there for some time, and then you can hear this recorded voice here. Okay, now what is the advantage here? Let's see first. Let me see if I can make you hear this. So this I recorded yesterday. Someone just did some exercise. Govindji, you have to tell me if you are able to hear this. I will start now.
Yes.
Do you hear the sound of heart pumping, releasing the blood, taking the blood again?
Yes.
Okay, so what do I make out of this? I can put it in this Think Labs Wave app, and I can directly count this spike. Okay, these spikes where you're seeing here, heart is pumping, and that sound dun, dun, that is coming. You have to actually increase the volume to very high levels if you want to clearly hear this. And simultaneously, I can also see this. I can also see the frequency spectrum of this sound. You can measure heartbeat, which of course you can measure by putting your fingers on your pulse. But in this way, I can record it. I can send it to my doctor, and I ask him if this everything's all right or not. Okay. In fact, when I recorded this, I sent it to my doctor friend, and he said that you should get that person checked because it looks like this is higher than usual heartbeat. So I have advised, actually, this is, I have advised the person to actually get it checked. Okay. So you can actually, what you can do, you can do some exercise, you can sit down at rest, and you can compare these heartbeats, and then that will be a nice activity for you to perform in the class. This method is described here in this paper. You can note it down if you are more interested in. This is actually called phonocardiography. Okay, from phone, you are doing some cardiac experiments here, hence this is called phonocardiography. People have actually gone one step ahead, and they are also using ECG on a phone, which is called electrocardiography on a phone. So the next one is frequency measurement. You can measure frequency of sound falling on your phone, and for that I'm going to use Arduino Science Journal here. if you open Arduino Science channel, you can see this. You can click on add sensor, and on sensor, this music tone icon that will give you frequency of sound falling on it. And I will show you the video of it, how to see this thing in action. Okay, on right side, there is an online piano which I'm playing. And for middle school level kids, this is going to be one of the assignment for you. So please pay attention to it. On the right side, as I said, there is an online piano app. You can also use something called Simple Piano or something called, there are lots of hundreds of piano apps. This I'm using actually on laptop because I didn't have another phone. And the left side, the screen of my Arduino phone. So I will be playing these keys. Okay, so you can see on y-axis, this is hertz. Okay, this is frequency. On x-axis, this is the time stamp which is going on. So as I'm hitting this note, I am seeing the frequency being measured in real time. I can go to this recorded data. I can go to each timestamp and then I'm measuring this frequency. You can see the first frequency was 131 hertz, and the second one was okay, so fourth one was 175 hertz, then 196 hertz, then 220 hertz, and so on. Now, what's your assignment here? Your assignment is to download this app, use another phone, and then use Arduino Science Journal to record the frequency as you are hitting different music tones. Now, I want you to get me the relation how this frequency is changing. You can see there is some pattern here. Okay, these are not just random frequency that after 147 something like 220 is coming or something. If you are going in a step, you will see some pattern here. So I challenge you to get the relation between these frequencies, how these frequencies are changing. Is there a relation at all or not? So this is some instrument. What can you guess? This frequency pattern which I have observed, who is singing here? Dr. Lakhotia, you are a musician, you are actually singer. So any guess here?
Yes.
Tell me.
So first it's B flat pitch.
You're talking about the third one, right?
First one.
Oh,
It's written
first
over
one is
there.
just
It's written over
first
there.
one is just random.
Yes.
Second one is of course piano. What I'm asking this third one. So second one will leave it to the student. they should figure it out because you will of course know what is the relation between these frequencies. What I'm asking, the third one which you are seeing, you can see this also looks like some music tones here. So who is singing here? Can you tell me the name of the singer? Okay, it's a difficult question actually. Okay, I think I'm overimposing on you.
Low pitch or high pitch, you mean to ask?
Yes, yeah. Can you comment on this? This
So it's
generating these kind of pitches.
male's voice.
Uh, is it is it very difficult to generate such a high frequency in music, in a vocal?
Yeah, there is a range to which
Yeah.
our vocal can reach.
So I assume that this is not an easy task to generate these frequencies. Okay. And also in this symmetric manner. Okay, they are very. This looks like that person is always hitting right chord. So let's see who is doing this. Okay, so this I actually recorded in my backyard. I went to this music tone. Now no price to guess. Such a beautiful voice. Okay, so this was actually Kuku's Koel's, Indian Koel's voice. I actually recorded in my backyard. I'm blessed with presence of lots of birds here. And you can see every time she is able to hit the right chord. I think a musician will agree with me here. A singer who does lots of jazz here will agree with me here that she's. So in the beginning, actually, you can see they're almost very close to 1,800 hertz. And every time she was able to hit the proper one. So this is another exercise for you. Explore the nature using smartphone. Okay, look around you and see if you can record the voice of crow. I have observed that crow actually sometimes it generates the frequency range between 400 to 500 hertz. And when they speak, when they are saying something, it is always in that frequency range. It's not like us, which we have lots of modulation in human voice if you are just talking. But when they are giving a call, it will be in very narrow range. That's what is happening with you. Okay, so this is just like fun exercise for you. Now I will come to the, this is related to nature and some kind of, biophysics things which I wanted to do. Now I want to focus on the some physics, I mean say some raw physics experiments here. There's something called inverse square law in light. I've been told that you have already done this experiment, but nevertheless, let me repeat it for you. It won't harm. A light source, when it generates in light intensity, and then it actually radiates in all the directions. The philosophy is this: if you take the model is this, if you take a point source, then actually it is radiating in actually in around a sphere. So I want to know that if you are at distance r from this source, then let's say intensity is I naught. Then what if you are at distance 2r from it? What if your distance is 3r from it? How this intensity of light is changing when you are moving away from the source? So since this is radiating in 3 dimension, so I'm covering sort of the surface area of a sphere to collect these photons. The surface area of this sphere will be in which it is able to radiate is 4 pi r square if you are at distance r. Okay, the power is defined by energy per unit time, and the intensity here is actually power per unit area at distance r, can be written something like this. So you can see when you are moving away from r to 2r, now you are in a sphere of radius 2r. When you are at 3r, then you are in a sphere of radius 3r. So when you are moving away from r to 2r, the I will change by, let's say that it is at r, it is at I naught. What will be at 2r? It will be 1 by 4. At 3r, it will be I naught by 9. So let's verify this experiment quickly. I will not do much plotting here, but I will show you the experiment which you can verify very quickly here. The simple measurement which you can take again on left side screen, right side my phone. So what I'm using as a light source, another phone. I've switched on this torch. So I've kept it at distance r, and on the phone, which is at on this table, I'm measuring the light intensity falling on it, and you can see it is close to 6,000 lux. Lux is the unit to measure the light intensity. Then I increase the distance by 2r. These are just equidistant pipes, which actually I've got it from toilet roll. And then it is 3r. The number will come out to be close to 617 lux. I pause it. I go to this recording and I measure the values. So whenever it was a distance r, the value was how much? 5,800 hertz. Sorry, lux. I'm sorry. And then 1560 lux, and for third one, it was 611 lux. Okay. So first time when it was at r, initial intensity was 5,891 lux. When you move to 2r, okay, when I increased one more pipe here, this was 1542 lux. Okay, when I was at 3r, then it was 617 lux. So if you divide IR by 4, that will give you 1472 lux. If you divide IR by 9, this will give you 644 lux. Okay, so these numbers are very good. As I said, this is not always good for precise measurement, because when you are covering it using another pipe, you are actually letting lots of stray light also to enter on your phone. So these readings may not be very accurate, but if you can take good care of that to removing that noise, results will be very surprising. You can go for lots of distances here, and you can plot r versus r square versus I data here, and you will find that it will be a straight line. Okay, now one more experiment. Actually, Govind, how much time do I have now?
20 minutes.
Okay, then I will do one thing. I will skip some of the experiments, and I will go to some experiments which are useful for undergraduate also. Okay, this experiment which you can perform at home again, it uses some concepts of mechanics. So when you throw a ball up, what it does actually, it goes up and it reverses its direction. It comes back to the ground. It bounces back again, and every time when it is bouncing, it is losing some part of its energy while colliding. So every time this height is decreased. Okay, let's say initial height was h0, then next one was h1, then h2, and so on. Okay. And the time difference between these two collisions, let's say there were delta t1, delta t2, etc. So our hypothesis is that each time when it is colliding through the surface, it is actually losing same amount of energy, E0 by E1, is equal to E1 by E2 and E2 by E3. What is E naught? E naught is mgh naught. It is just the gravitational potential energy which it has acquired by lifting it to the level h naught. So when I put mgh naught here and in E1 I put mgh1, then I will get h1, h naught by h1 is equal to h1 by h2. So h naught is this initial height, h1 is this height. So my assumption is that the ratio of these subsequent heights, they're almost same. And by applying Newton's laws, Newton's equations of motion, you can write h1 is half ut plus half gt square. U is the initial height. When it started falling from here, the initial height was, initial velocity was 0. So I can forget ut term and I am left with half gt square here. Okay, and there is no other attenuation here. So I can assume the time taken from ground to the top is almost same as from the top to the ground. So for the time from here to here, I can just take this total time. I cannot measure this time here. When did it started reversing? But I can always measure the time between these two collisions when it is striking the surface. Okay, I will take half of this time and then half of this time for h2, and I will get h1 and h2. If I divide these two, h1 by h2, and h1, I will take h1 from LHS to RHS, then this formula will come up. This is not very difficult thing to grasp. It is just 1 or 2 minutes of mathematical exercise. Okay. So if I know this delta T1 and delta T2, I can know what is the height at this when this started this journey. Now where I can use it? How can I verify this principle? So I'm going to use the app called Web Editor, and what this will do, when I will throw this ball up and when it is striking the surface, it will record that sound. So I'm actually using a decibel meter here. And every time it is striking the surface, it will keep recording the sound. And the end, I will see what was the time when I recorded this sound, what was the time when I recorded this, and so on. So I will have these values of delta T, this T1, T2, and T3, and so on. I will subtract these numbers. Let's say these numbers are these, and I will subtract these numbers, and I will have delta T1, delta T2. I will put back these numbers in this equation, and I will calculate this initial height. I want to measure the height of, let's say, a building. Okay, using this experiment, what will I do? I will throw a ball from here such that it reaches to the top and it starts its downward journey from the topmost point. You have to make sure that it changes its direction at the topmost point of that building. Okay, and then I just need to record this sound here. So I will show you this. Of course, I was not in front of a building. I tried to do this in a room in which it was not physically, it's not impossible, but difficult to measure the height of this one. So I have kept my phone on the ground. On right side, I am showing the screen of Wave Editor, and then I'm throwing this ball. Okay, on the right side, you can see how it is recording the sound of when ball is striking the surface. See it again. I will save this, and from let's see. Okay, so right now it is not showing you the x-axis, but on x-axis I can record the timestamp of every strike. Okay, I just need to see where I saw the peak of that and peak of that sound. So for this particular experiment, these numbers came out to be 4.26 seconds, 5.40, 6.24. Now look at the accuracy which you are getting here. This is actually, you can get up to millisecond using this device, up to millisecond accuracy. Okay, so this is actually, these kind of experiments are very accurate. sorry, these measurements are very accurate for this kind of action. Whenever there is a sound measurement, your phone will give you very precise measurements. So I will subtract 5.4 from 4.26, 6.24 to 5.4. You can also see that this duration is decreasing because every time it has less energy to climb up. Okay, every time it is losing energy. So it will come down faster. So as soon as it was actually the height was decreasing, the subsequent time interval also decreasing. You can put these numbers here, and I'm sorry, I have reversed these numbers here. This should be 1.14 and this should be 0.84. So I apologize for this typo. I put these numbers here, and the initial height will come out to be 2.94 meters. And the actual ceiling height was close to 10 feet, which was 3 meters. Okay, not a bad result for this demonstration. Now, this is an exercise for undergraduate students. If you are listening to me right now, you need to take a measurement of something by this method. Okay, go outside, try to take measurement of a building, try to measure the height of a building. That will be pretty exciting, provided you are able to secure the height of your ball to reach at the top of the building. Now, one thing I have to tell you for this undergraduate student, that you can use the magnetometer to measure the dipole moment of the magnet, and for that you can use the formula. I'm sorry, I'm in a hurry here because I think I'm running out of time. So the magnetic field as distance x from a magnet, if it has got dipole moment m, for the middle school level student, m is the measure of the strength of that magnet. It is called dipole moment, which you will learn about it in your higher secondary level physics textbooks. So m is the measurement of strength of that magnet. It is high, you will feel that magnetic field is also very strong. So if you are at distance x from the magnet, then the magnetic field will be mu0 m by 2 pi x cube. The mu0 is also a constant. It is called permeability. It tells you that how easily your magnetic field is actually being allowed in a medium. Now I can use a smartphone to measure the dipole moment of this magnet. What I can do, I can use Hall effect based sensor. I will use 5 Fox for this. I can keep magnet at different distance from this phone. 5 Fox will tell me magnetic field. So I can have the data of this x versus bx. Okay, if I take log of both the sides, then log bx will be minus 3 log x plus log mu naught m by 2 pi. Okay, this is not very difficult to do because these are all multiplication here. So every log term will be in addition, and this 3 is in denominator, so I put minus 3 here. So if you plot log bx versus log x, you have x, you have distance from the magnet to the smartphone, and you have magnetic field. So if you plot log of bx versus log of x, this intercept will give you the value of m. Okay, so I will quickly show you the how to do this. So on left side, the phone is kept on a floor, and I have kept a scale here to measure the distance x, and I'm opening 5Fox app. Right side is the screen recording of 5Fox app. I go to magnetometer section. Okay, I click this play button, then it will start recording the magnetic field. I have a magnet in my hand. I clicked it, it started recording. I keep it at some initial distance. And since I'm moving in x direction, remember this is the x direction in phone. That's how it is defined. I change the distance by, let's say, 1 centimeter. Then again 1 centimeter. You can see this change here. Earlier it was more than 800 microtesla. Then it is between 800 and 600 microtesla. Third time it was 600 microtesla, and so on. You can see, I'm getting a nice step shape magnetic field variation. I pause it. I remove the magnet, otherwise it may damage smartphone. Then I save experimental state. I can export the data to get it in an Excel file. I went to this BX. I can go on every point and I can measure the magnetic field at each point. Look at, you can see it is at right now. I have kept my finger here, so it is 911 microtesla. Then second time it is 727, then 586, 473, and so on. So what you can do, you can record this X versus Bx and plot log X versus log Bx to get the dipole moment of the magnet. Okay, this is the graph. So if it is a perfect 1 over x cube pattern which is magnet is following, then you will get a straight line. Okay, on y-axis this is log Bx, on x-axis this is log X here. Okay, and intercept, from the intercept you can calculate the dipole moment, which will come out to be, for this particular case, it is 11.52 ampere per meter square. Okay, this is the error part, which a middle school level student may not be familiar with. If you do lots of measurement, then you can take a standard deviation of that, those measurements you can take as the error. It means that my answer is as close as it can be between 11.52 plus minus 0.07%. It can be, my answer is in between these range. This experiment was further used to verify, to get the acceleration due to gravity, which I am not describing here. I don't have much time. Govind, shall I just wrap it up?
You can take one more.
I can take one more. Then I will take that maybe speed of sound. Okay.
Yes.
Okay. This I'm picking up this from the problem which I wrote for this year's Junior Science Olympiad, which was held in month of January. You know that I'm also assisted with Olympiad program at HBCSC, and this was the problem posed for a student who have crossed level 1 and they are entering for level 2. So this problem is available on our website. You go to Olympiad, Science Olympiad page on HBCSC, go to question papers, and you will find this year's paper. This problem, you can see a signature of a smartphone. The problem is as follows. It is, I think, it's a wonderful problem if you want to check the concept of a student of if they have any scientific ability or not. So let's see. So there is a Fatima and Bharat. These friends, they are clapping. They are at distance d from each other and they start clapping. Now this wave editor app, which I just used to record this sound intensity, which I was using in dropping magnet, that records the intensity of sound when they are clapping. And Fatima's distance d, Bharat is on right side, and on this black and this white peak screens, they are actually the screens of wave editor app. So when Bharat claps, you will see a large peak here. Okay. Then the sound takes some d by v time. V is the speed of sound to reach to Fatima. And Fatima will record some faint peak here because intensity of sound has decreased as it has traveled up to Fatima. Then after that, Fatima claps. So since she is clapping near her phone, so the peak recorded in her phone will be a larger one, and it travels back to Bharat. And then peak in Bharat phone will be smaller one. And you can see we have given timestamp here. Okay, because student didn't have a smartphone, so I have given the timestamp for every event. And with this information, these two people have deduced the speed of sound is 363 meter per second. Now the challenge was to obtain the distance d between them. This was the problem. Now what was not told to them, that who is clapping first. This is the first thing they had to deduce. Just by looking at this graph, one has to figure it out who is clapping first here. If Fatima is clapping, and you can assume that she is clapping very faint here. If Fatima is clapping, then her clap is very faint. Okay, it is very small peak which you are seeing here. If it takes time D to travel to Bharat, then this peak recorded in his phone will not be as larger than Fatima's peak, because it is a Fatima's clap which has traveled up to Bharat. Okay, so this thing you rule it out. Now next thing you have to figure it out. So here at this time you actually conclude that Bharat is the one who clapped first, because Bharat's peak is higher here, then it is traveling to Fatima, then peak is actually smaller. This is the very important part of the problem, to figure it out that who has clapped first. And when you look at this timestamp, since Bharat has clapped first, the first time which was recorded 6.615, it takes some time to reach to Fatima, and it is 3.037 seconds. Okay, 6 सेकंड पे उसने क्लैप किया, 3 सेकंड पे फातिमा के पास पहुंचा, देन फातिमा ने क्लैप किया 5 सेकंड पर, इट रीच on 8 सेकंड इन भारत स्क्रीन. इज इट पॉसिबल 6 पे क्लैप करे कोई और 3 सेकंड पर यहां पहुंचे? इट इज डेफिनेटली नॉट पॉसिबल. What do you figure it out of this? It means that Bharat has started his phone sometime earlier than Fatima, because both screens are in two different phones. So they are at liberty to start, liberty to click, to hit that play button at their will. So this is the second part of the problem, where they have to decide. So nothing was told to them, but they have to deduce first who clapped first. Then they also have to realize that these clocks are not synchronous, they are asynchronized clock. It was one of the most challenging part of the problem, and let me explain it to you again. So in Bharat, on right side there is a Bharat screen, left side Fatima's screen. So when Bharat claps, this will be the peak, the highest peak here. It takes d by v time. D is the distance between them, v is the velocity of sound. It takes d by v second to reach to Fatima, in Fatima's screen. And after some delta tf time, Fatima claps. So this peak number 3 is recorded. And it takes again d by v time to reach to Bharat's screen. So this is the fourth event which was recorded. So time difference between these two peaks is delta TF, and this is delta TB. Now this cannot be same, because it took some extra time from 1 to 4. So between 2 to 3, it is just by what time difference Fatima has clapped. But for Bharat, that also takes into account the time sound traveling, time of sound traveling from Bharat to Fatima and then coming back to Bharat's screen again. So there are 4 events in the problem. So if you note down all the events in the problem, the first time will be time taken from sound to reach from Bharat to Fatima, plus this delta TF, then plus time taken from sound to reach from Fatima to Bharat. So this is 3 to 4. So there are total 3 time differences here. What you have in hand is delta TB. So since these clocks are asynchronized, I can always subtract the time from Bharat's screen and Fatima's screen. So when I'm taking the time difference in their time frame, that will not be a problem. But if I take the time difference from Bharat to Fatima, that will be a problem. So I'm at liberty to take this delta TF and delta TB as the true value here. So delta TB will be d by v plus delta TF plus d by v. So this is delta TB, this time difference is equal to d by v plus delta TF plus d by v. So ये 3 event मिला के that will give me total time duration, and where v is the speed of sound. So once you figure it out, there is nothing else in this problem, because you can just take v to the left side and the answer will come out to be 2d by delta tv minus delta tf. Okay, what was given to you? This the time of these peaks, which you can subtract, and you can calculate delta TB and delta TF, and that will give you the value of so that will give you D here. What was asked in the question, yeah, to D. Now what I want you to do is to calculate the speed of sound. Okay. So because what you can calculate is the distance between you and your partner. So you can have one partner at the end of your room. Let's say you take some larger distance, but this should be a quiet environment. You ask your other person to switch on this web editor app, or and you also switch on web editor, and then you first you clap, and then you see the peak in your phone. Then immediately after you, other person should clap. Okay. By these two peaks, you can measure the time period, and you can subtract these, and then that's how you will calculate the velocity of sound. You already have D. If you are doing this in your room, then D you will know, and delta TB, delta TF you can get from your phone. But I will want to make this your life bit simpler here. I want to use another feature of Firefox app. It is called acoustic stopwatch. What it does, okay, what it does, it actually measures the time difference between two sound peaks. It automatically gives you that. You don't need to go to web editor and do that. So when I will, so it's like some kind of acoustic stopwatch. I clap once, means I start the watch. I clap twice, I stop the watch. Look at this. So time difference between these two claps was 2.71, and now it is 2.019 seconds. So that delta TB and delta TF, which I'm talking, they are already given to you on your screen. So you can ask your partner to start this acoustic stopwatch in her phone, and you also have your acoustic stopwatch in your phone. Both you switch on, then you play this, you click this play button, then you clap, your clock will start, and his clap will also start. Sorry, his clock will also start. Then he claps, and then both clocks will stop. What you have in your hand after these two values, so this time which you are seeing here, these will be the values of delta TV and delta TF. Okay, and these two values you use to calculate the velocity of sound. Now, Govind, I don't think we can conduct it here because it will take another 15 minutes. Okay, so I will leave it to the students to exercise this at your home, and then if you want to submit it to me, I will be happy to have a look at it. Okay, this problem is there on, as I said, HBCSE, Homi Bhabha Center for Science Education's Olympiad section. You go to Junior Science Olympiad paper of this year. Solution is also there. In very detail, I have explained it here, so you can have a look at it. Yeah, so this is the assignment. Sorry, I already told you. Stand at some known distance deep from each other. Assume one of you is Fatima, other one is Bharat, and then start acoustic stopwatch, and then obtain the speed of sound V in the median. Let's see how accurate result you can get. You should get close to 340 meter per second, but result will not be very good here because some voice, some stray voice always land up your own phone. But nevertheless, it should not be less than 300. It should not be more than 400 meters per second. Let's see how accurate result you can get. Alternatively, you can always use web editor. That will be actually, I always like that part because that tells you, you will not, then you are not using acoustic stopwatch as like a black box. You are reducing something else. You are making one more measurement from this experiment. Okay, this is the last slide. I started with some simple experiments, something just to explore the basic sensors in a phone. Then I slowly, jacked up the level of this experiment to hardcore physics experiment, which you can perform in physics lab. That can be also used as an experimental problem for the student. But people have not stopped using it for the benefit of the society. Oh, by the way, this I forgot to tell you. You want to measure the oscillation period of a pendulum, just fix your phone to this string, or you can hang it to a thread. Then you can record acceleration. Okay, start accelerometer, and these peaks will tell you the distance between, time distance between, time difference between each oscillation, and that's how you record acceleration due to. You can also get acceleration due to gravity. You can have length of the pendulum, etc. Okay. In 5-Fox app, there is one section called Pendulum Lab. You're welcome to check it. Uh, have you ever wondered that if you drop a water drop on your screen, on your phone's screen, you if you see carefully enough, that's how it will look like. Okay, these grids which you are seeing, these are the pixel of your screen, and these colors which you are seeing, this is coming because of reflection of through the water drop. And people have used this to calculate the density of that drop. Okay, it's a wonderful experiment. This is a very recent experiment. Many times I thought that this can be always used as a lens, but they have gone one step ahead and they calculate the density of this water drop. You can use it as a spectrometer. This is just low cost spectrometer. This is also very recently, it has come in the phone, in the journal. And in last, I can tell you one more exciting experiment. This is the ECG, electrocardiography, using a smartphone. Same people who have developed this electrophonocardiography, they have also come up with this idea. You take 2 tablespoons, some coffee spoons, and connect it to the headphone wires. Your microphone in your headphone actually converts your sound signal to the electric signal, and it goes into your smartphone. And your smartphone doesn't read actually sound signal; it actually reads this electric signal. So every signal is an electric signal for it. So when you are using these spoons, you are transmitting the small electricity from your body to this spoon. As your heart is, pumping, some kind of electric signal is being generated. Very faint electric signal is being generated in your body, and through this finger, it is actually being transferred from this spoon to this headphone mic, and it is being fed into this smartphone. Now imagine this: you have ECG in your hand. Actually, devices have already come up, but this is just low cost instrument which they have tried to see. I have tried to replicate this, but I could get some value, but it's not very fine, so I am not showing it here. So that's all, folks. To summarize, these smartphone sensors, they open the possibility of novel ideas, and they also bring innovations in the traditional experiment. Is something, if you are bored of it, use a smartphone. And probably for teachers, this is for the teachers. Your students will be, excited to do these experiments when they have to use a smartphone. Another reason to bring a smartphone in your class. And they do not compromise with the experimental skills. It requires enough level of experimental skills. And there are more than 400 published papers on this use of a smartphone in these journals. So why you should be left alone? You should also do these experiments. And it is, of course, no cost, almost no cost. Of course, something you have to pay, but the major part of the experiment, you don't have to pay for it. And these are some references. There is one paper which we recently published using smartphone. It is here. Other paper is not listed here. That is also soon going to be come up here. I'm sorry, that is not listed here. These are the apps which I have used in this talk. And in this website, this iPhysics Lab, lots of resources here. And the person who has written this 5-Fox app, Westin Stocks, this is the paper here. Okay, so thank you very much, Govind. I will stop here, and I'm ready to take questions if they have.
Yes, thank you. Thank you very much, Dr. Pathak. It was really a wonderful session for students as well as for the teachers to explore nature, to explore science around us during this lockdown period. Within a very short time, very short period, you have covered many topics. You started with reaction time, then heartbeat, then you have given the sense of frequency to the audience, and even you played with the intensity of light, then bouncing ball activity, which was very good, and many more things students can find by using these apps. And I hope We'll definitely take advantage of this session and we'll explore many things around them. Now I invite students with their questions. If they have any questions, they can join our Zoom room. Details of the Zoom room is there in the chat box. You can, those who have joined the Zoom room can raise their hands for further interactions. You can ask your queries.
I think Govind, it is running late on YouTube. So
Yeah, need to wait for a few seconds. But I can see 20 students are there in the Zoom room. If they have any question, then. So it will be there, this session will be there on the same link. You can check out the things. You can see the session. You can watch the session again and again. All demonstrations were crystal clear, but still if you have any doubt, Dr. Pathak will be available through his email ID.
I will leave my email ID in chat also. And actually, I will share the, can I share the first page of a screen that will have my email ID?
Yeah, you can. If you don't have any questions, then you can give your feedback. How do you find this session? Students, you can raise
That I
hand.
think you should take anonymously or in my absence.
If they have anything in their mind, they can ask.
Yes, please ask. Will
Emails
using
of
magnet to
Taneja ma'am
closer
is
to your,
there.
okay, Aniket has asked, will using a phone magnet too close to your smartphone will it damage our phone? Yes, if only if you go higher than 3000 micro Tesla, then it might damage your phone. So just be careful of this. When you're measuring the magnetic field, if you use, let's say, if you don't have a smartphone, sorry, magnet at your home, you can use those magnet stickers which you use for fridge. Those, if you just keep it even on your smartphone, it will not damage anything. So just be careful, not more than 3000 or 4000 micro Tesla.
Sir, I
Iris
have a
Taneja
question.
ma'am. Yes, ma'am.
Yeah, Mr. Pathak, this was really enlightening because I had tried exploring smartphone apps and did some experiments, but I faced an issue with magnetometer sensor app where I was not able to locate where exactly the sensor in my phone is located. So the way you had placed, it was like on the right side, on the upper part. Is there other magnetic sensor in our phones located? How do we locate that?
Yeah, actually, it is very important part of that activity. And I apologize that I did not stress it out, but that is actually most important part of that exercise. You have to locate the magnetic sensor on your phone. So what you do, you take the magnet and move it across the length of the magnet first, and then you see where it is going from higher to lower, where it is changing its sign. Okay, then you, so that's where you can fix the x, sort of x axis origin. Then you move it across the width of the phone. Okay, तो आपने एक बार x डायरेक्शन में खिसकाया उसको, then एक बार y डायरेक्शन में खिसकाया, where these 2 points are meeting, that will give you the origin of the phone. Is it clear?
Not exactly, but I'll try.
I will tell you. Let me explain it to you again.
Yeah.
You place the magnet slightly away from the smartphone. So you put your phone on the floor.
Yeah.
Then at the end of the phone, towards the bottom edge of the phone, you place the magnet. Then in a straight line, you move it across. You go up. towards the upper edge of the smartphone. As you are moving from bottom to upper side of the phone, you will see the change in sign of the magnetic fields at some point, because you are crossing the origin. So while you are going from going along the y-axis, you are crossing the origin. So you will see, notice the change in sign. तो जहां पर भी आपको change in sign मिल जाए, there you mark. Then you move to the other side of the magnet. So once you go along the length, the next side, next time you go from the along the width. So there, wherever you are seeing the change in sign, you may cross these 2 points, and then you can that will be the point of your origin. Actually, I can send you the paper on that. That will be probably easier for me to tell you.
Oh, thank you so much.
Okay,
That would be
just
very
send me an email. There it will be. I will be. Their actual method is described in well.
Sure.
Okay,
Thank you.
someone asks. Yeah, thank you. You're welcome. Someone say that how can I make the spectrometer by using a smartphone? So people have used actually some kind of grading experiment, and then you can also use trace paper. Best I can tell you, I can send you the paper which I just described you. That will be better. So again, you also send me your email, and there the method is described in more detail.
Yes.
Someone asked some of the functions. Yes, you were saying, Govind, something.
Next in is Ronak. Yes, you can.
Yeah, Ronak नहीं पूछा था ये spectrometer.
Okay.
Someone have sent me direct message. Some of the functions are not working on my smartphone. What can be the reasons? It may be because you may not have those sensors. If you have bought your phone in last 1 year, except for pressure sensor is only in the high-end smartphone and thermometer like iPhone or Samsung Galaxy S2. Those phones have those sensors. Otherwise, accelerometer, magnetometer, frequency is very basic, that should be there. So if unless your phone is very old, I don't see any other reason. Maybe you can uninstall it and check it again, or you can if it is not working in Firefox, then you can use one more app to check. So you use Firefox. If it is not working, you check Arduino Science Journal. If it is not there, then you check one more app called Physics Box Tool Sensor. That also you can check. So you try various apps. One of them it should work. Otherwise, your sensor is one faulty. Okay, someone is saying, praising that. Thank you very much. Arnavi. Yes, one more question, Ronak. Please go ahead. Maybe
Sir,
you can unmute yourself and ask.
Sir, good evening, sir.
Yeah, good evening.
Sir, I have a question that the cardiometer that you have told to make us. Sir, is the reading of that cardiometer is precise or very?
So you are saying the heartbeat one?
Yes, sir.
Yes, it is very much precise.
Okay.
But you have to be careful that you may not be able to. You should not be confused stray sound with the heart sound. There you should identify it closely. Okay, but the warning is always given: do not use it for the medical purpose. Okay, do not use it for the medical investigation. Thus, use it to for the as an exploration activity. You can use it, but whenever you have to use it for medical investigation, go to a proper doctor and use it.
Thank you, sir.
Yes, anyone else from students?
I think YouTube is almost ending, so probably if there are questions,
Yeah, they are. Most of the messages are there to thank you.
Where are you seeing? I'm not seeing anything on YouTube. I'm actually only seeing
On
the last message which I see is from myself. Is there any undergraduate student there?
Yes, I invite Arnavi. I can see you there. Arnavi, do you want to say anything?
Yes, sir. I would like to give a feedback. Am I audible?
Yes,
Yes,
sir.
you are.
Sir, this was a really great session. I have learned a lot, and I know all my classmates have also done. Uh, in this lockdown era, in this COVID pandemic, everybody has already learned so much good dimensions of a smartphone. But today we have learned many more, all that sensors which exist in smartphone and how can we use smartphone in some sort of study as well. So thank you for such great session. All your practicals were crystal clear as Lakhotia sir already said, and I have learned a lot. Thank you.
Thank you, Annavi. I want to stress out one more point that my interest in a smartphone actually started during lockdown only, because we wanted to do some physics. What could we do? So we just started exploring them. That's how I came up with this. One more question, Neeraj, Taneja.
Yes, ma'am, you can. Now you can speak. Neeraj, ma'am.
Okay. Sir, one more thing if we have time. So in fact, my interest also was during lockdown and experimented a lot with these phones. Maybe my phone was old at that time, but one more thing, sir, like the speed of sound experiment or where you use acoustic stopwatch, there was an adjustment to be made in terms of the reaction time or something. There I struggled. So any idea on that, like how much should be that time set?
Just a minute, I will open that.
Because I was getting different speeds every time I did the experiment, 5-Fox acoustic stopwatch experiment. I was getting different times and hence the speed.
Okay, so that's why actually, so here this threshold and minimum delay, right?
Yes.
Threshold is to avoid any stray sound to be assumed as the proper signal, you have to play with the threshold. If you keep threshold very low, then even a small sound will start and stop your watch.
Yeah.
So you try with some values, clap it and see if it is recording or not. Okay, so let's say that you started the clap. अब बीच में कोई छोटा सा sound आ गया. Let's say someone is sneezing or someone is coughing. That sound can also stop their watch. So probably some stray sound is coming and giving you some wrong values. And this minimum delay, that I think that you don't need to worry about. That you can just leave it. I mean, that you do not. You started so minimum delay. If you say, let's say I start with after 1 second, then you will start after that. So that you can just leave it like that. But threshold is very important here. That's why I used actually wave editor. That is very clear.
Okay.
There you can see every peak, and there you can even if there is stray sound, you can identify whether there is stray sound or not. Okay, तो वो आप करोगे ना तो उसमें आपको ज्यादा एक्यूरेसी भी मिलेगा.
Yeah, that's what I feel.
Well,
I think one is not here.
yeah, I got disconnected. So with this, we can end the session. Yes, thank you very much, Dr. Pathak, for your valuable time with us. I hope students can do miracles if they can explore all the apps and they can find something new during this lockdown. Thank you very much for exploring all the applications. In future also, we would like to connect you for some other topics. We are aware of your expertise in science education. And yes, thank you everyone for joining us for this session. Please take care, use masks whenever you move outside, sanitize your hands and take care of each other. Thank you very much. With this, I would like to end the session.